Hey everybody, Mr. Munson. I'm glad you're here. Let's take a look at critical points. Extrema is another phrase that might be used or word be used what we're looking at. So suppose I had some function f of x here and it kind of wavy, has these valleys and hills and valleys and hills. What we want to do is be able to understand some vocabulary words, but also what's it mean and how to find these things, right? So this would be what we call a relative or local minimum. And this is a relative or local maximum, and so on, right? Now, for the term general maximum, or a general minimum would be where a graph is like this. If you notice, this graph has no bounds. It continues to go up and get higher and higher if it goes this way and lower. So there is no maximum height that this equation is going to go to, nor is there a maximum low. But a graph like this has a maximum high. This is as high as it's ever going to get. And so this would be seen as a general maximum. It's the ultimate maximum. It has two local maximums, but that's the general one. That one is a higher version of that, okay? All right, so looking at this equation here, I would want to know if I could find these critical points, which we're going to call local minimums and local maximums. If I use the word relative minimum, relative maximum, I mean the same thing. So to find these points, I could go to a graphing tool and have it help me find those. So let's do that. Now I'm going to go ahead and go over to a graphing tool and use a procedure to find a minimum and a maximum. It's not going to be this equation, but it'll be another one. And the process is still the same. I'm just going to create an easier equation for us to look at and deal with. Let's go look at how to do that.
Okay, so what I'm going to do is I'm going to go in and use my TI 84 Plus emulator that I have on my computer, and you can look online to see how do you do this. It's pretty slick. So I'm going to turn it on. I'm going to go to my graphing tool for this calculator is found under Weigel's key, and I'm going to enter in that equation that you see there. I'm just going to, whoops, I'm sorry. Let's get in there. There we go. So we're going to do x. I'm going to use the exponent tool there and cubed. I'm going to go ahead and hit my arrow key to get out of that. Then it's going to go plus 3x. I'm going to go ahead and hit my squaring tool over there. Whoops. All right. And then we'll square. How about if I do that one squared? Plus 4. Okay. Now I'm going to go ahead and before I hit it, I'm going to hit zoom. I'm going to go ahead and hit 6 for just Z standard. We'll see how that turns out. That's not so bad. Looks just like that. All right. So now what I want to do is I want to find, using my calculator, where that maximum is and where that minimum is. I got a really good suspicion where that minimum is. I'm thinking it's at 0.4. Now I'm going to show you a slick. I'm just going to put. I'm going to go in here to zoom, and I'm going to take this point. I'm not sure if you can see. I'm just tracing it. I'm just going to kind of put it up in this hot area and let it zoom in that general area. Hit enter, and there we have it. Perfect. So now what I'm going to do is I'm going to use this calc under trace function to help me find that maximum minimum. And so I'm going to look for that maximum there. So I'll go ahead and select 4. And what I have to do is I have to put my cursor here, usually left to right. I put it to the left of it, hit enter, and then now it's asking for the right boundary, the other side of the hill. Hit enter, and it's asking me to guess, so it just helps it predict it. So I'm just going to put my cursor, you can barely see it, put my cursor at the top of what it looks like the top of the hill. Here we go. right there, right around there. And so it's kind of helping it think, okay, I think I got a right answer when it comes up with it. Hit enter, and there's my maximum. So I know that that maximum, we'll just call that 2, happens at -2, comma 8. Okay? Now I suspect this minimum's at 0.4. Let's just double check. Let's go for a minimum, which is number 3. And we'll go down here and do the same thing. Start on the left. We'll give it kind of a boundary here to kind of be looking at the data, where it's going to look at the data in between here and find where the data is decreasing as my x gets larger and then suddenly increasing, and someplace in between there is going to be my minimum. So I'll just put it down here, hit enter, and sure enough it's at 0.4. Okay, so that's how you would do it on a TI style calculator. All right, let's take a look at our function here that we plan on working with. I'm going to call it h of x. And I'm just using Desmos here as a graphing tool. So let's type in this function that I want to work with. It's x cubed plus 3x squared plus a 4. All right. So what's kind of neat about Desmos is it actually comes in here and gives me my critical points right off the bat. I don't have to do much finagling to find it. So I get these points right away. It also gives me other critical points like the x-intercept, and in this case the y-intercept is the minimum. So I know that the local maximum here is at -2.8 and the local minimum is at 0.4. Pretty easy stuff.
Okay, that's not too hard, especially with that type of tool or those types of tools at our hands, okay? So once we know what these critical points are, we can identify them as, our local and relative or local extrema, okay? So let's do that real quick. All right, so we have a maximum here at this -2, and through some process, I'll just say that it is at 3, and I'd use a graphing tool or whatever to figure that out. And then I have another maximum over here, another relative maximum at this point. And then let's look at the minimums. The minimums are coming in at -5, and 3 comma, we'll say 1. So that's how I identify those. Those are my maximums and these are my minimums. Now what we know is to the left and to the right of those, the graph is either increasing or decreasing. And if we understand that about what's happening to our f of x values as we move left to right, if we see that as my x goes higher, so does my function, then we call that increasing. So if you think about it, if I have a f of x evaluated at -4 and it's this value, and then I look at f of x when x is -3 and it's a higher value, I can tell by that data f of x -4 is a lower number than f of x -3. It means as I'm going left to right, it's increasing. I could see that same data over here if I was to evaluate my function at different values along my graph over here. So we know this is increasing over here as well. We know that if we looked at the f of x values over here, that as we move left to right, that as my x values go higher, they get more positive as I'm going this direction, my end result of my function is decreasing numbers. It's going lower. So we would say that on this side of that minimum, it's decreasing. Now this is what I just discover if you think about it, that if I have values and I can see they're decreasing, and at some point, not known to me, I can see on the other side the values are increasing for f of x, then there must be a low point. At some point, it must switch from decreasing to increasing. And that's going to be a minimum value. Minimum values always fall between a decreasing, reading left to right now, decreasing values to increasing values of your function. Interesting enough and easy to decide or see that it's a decreasing function. I'm sorry, it's a maximum value that happens when you have your f of x values increasing and then suddenly decreasing. That creates a maximum value. So if we're looking at data and we can see the numbers for our function are going up and then going down, there must be a maximum value there. Again, decreasing then becomes increasing, decreasing becomes increasing, and sure enough, there's a minimum there. And over here, I can see my graph is decreasing as well. Okay, so let's just mark that on our number line here for these. I have decreasing and then increasing, decreasing, increasing, and then finally it starts to decrease as it approaches infinity. It continues to go in the x direction towards infinity. Negative infinity, the y goes, but my x's, as they go to negative or goes to infinity here, so does my graph continue to decrease. Okay, so let's write some intervals for this. Now this is, I'm looking at this over the open interval. If I was looking under a closed interval, instead of looking at the entire graph, I was simply looking at a short closed interval of the function. Then in that interval, there is a maximum and there is a minimum, but it might not be coming through because of this increasing, decreasing representation that I've just talked about. In this interval, there will be a number that's high and a number that's low, but because it's in a closed interval, you might not see that differentiation that's happening. So we're looking at the open interval. Let's go ahead and write up what our decreasing and increasing intervals look like. So from negative infinity up to 5, not including 5, that's where our minimum falls. That's a decreasing. From negative 2 to 3, another decreasing set. And then finally, 6 to infinity. As my x's go 6 to infinity, it's a decreasing segment of my equation. Let's look at increasing. Choose a different color here. All right, increasing happens between negative 5 and 2. And between the interval, open interval of 3 to 6. All right. So that's how I, note the relative minimum, relative maximums, decreasing intervals, increasing intervals. So I'm going to have you put me on pause. I'm going to give you a different problem and ask you to go and graph it and to find the local minimums and maximums, if there are any, and then write out the decreasing and increasing open intervals. Okay, put me on pause, or I guess I have to put up the problem, don't I? Here we go. Okay, so this is your problem. So what I want you to do is go ahead and graph that, and I want you to find the relative maximum minimum, make sure you use proper notation here, and the decreasing and increasing intervals. Okay, so go ahead and do that. You definitely want to copy the graph into your notes so that you have it as a reference point. All right, go ahead and put me on pause, come back and check your work. All right, let's look this over and see how you did. First of all, here's the equation that I gave you. When I went to my graphing tool, this is what apparently it came out to be. Quite predictable, actually, now I think about it, because my leading coefficient on my highest degree term is negative. So as this term goes, x values go in here that are getting more and more negative, this becomes a very large negative number, but then this tells it to take the opposite of it. So it becomes a very large y output, positive y output. And the other side is true over here, that as this number, a positive number is put into here, it becomes a very large positive number. And then this minus turns it into a very large negative number. These have an input, but not too much. But as you can see, my y decreases there. So my maximum value, relative maximum value was there, and then the minimum was here. My decreasing and increasing intervals, open intervals, were written here. Use a union symbol to represent that it's this interval and essentially this interval and any other sequential intervals that might encounter in increasing or decreasing area. Well, that's critical points. So I hope that was helpful. Let's see you next time.